Hello and welcome to this demonstration of the ANSYS fatigue module. Today we'll be looking at the fatigue analysis of a simple formula SAE hub. For this study, we'll be constraining the bearing portion of the hub and applying 300 pound-feet of torque onto the faceplate of the hub and also a dead load of 150 pounds shared between the various bolt holes on the hub. The objective of the study is to find out the number of cycles before the hub experiences fatigue failure. There are two types of fatigue analysis that can be performed. One is the stress life fatigue analysis, and the other is the strain life fatigue analysis. The stress life fatigue method is more suitable for low strain, high cycle fatigue analysis, where the stresses experienced by the part from a single loading event is much smaller than the yield stress of the material. It's based on empirical SN curves, where you input the alternating stress values versus the number of cycles to fatigue failure. The strain life fatigue method is more suited for cases where the parts experience large strains and the stresses can exceed the yield stress of the material and thus result in plastic strains. Typically, we are looking at fatigue failure within a few hundred cycles. With that, let's move on to the actual demonstration. So I have a blank workbench project page open. Let's make sure we have the correct unit system of US customary inches selected. Next, I'm going to insert a static structural analysis onto the project schematic. Let's review the engineering data to make sure the required material properties have been defined. Go ahead and edit the engineering data. The default structural steel already has the alternating stress versus the number of cycles or the SN curve defined for the material, and the default interpolation scheme being used is log-log. So this tells ANSYS what to do if a particular stress falls in between two defined points on the SN curve. So you can choose between log-log or semi-log or linear interpolation. Typically, you would want to use the log-log interpolation. As you can see, the strain life parameters have also been defined, so we can choose either of the methods depending on what stresses are being experienced by the part. Okay, let's go ahead and close engineering data. Now we need to import the hub geometry. So I'm going to just browse to a step file, and then we can go ahead and edit the model. The part has been assigned structural steel material properties. Let's quickly review the global Cartesian coordinate system. The y-axis is the axial direction of the hub, and the x-axis is the vertical direction of the hub. Now let's go ahead and generate a mesh quickly. By default, ANSYS is generating a tet mesh on the model. If we want a hex dominant mesh, we can insert a mesh method, choose the body, click apply, and then choose the multi-zone mesh method. Let's go ahead and insert loads and boundary conditions. I'm going to first insert a fixed support on this face to represent the bearing surface. Then I'm going to apply a torque or moment on this face, and I'm going to use the component method. I know that the y is the axial direction, and I'm going to apply a moment of 3600 pound-force inches or 300 pound-feet of torque. Next, I'm going to select one of the bolt holes and then go to size and select all entities with the same size. Now, as you can see, it has selected all the 8 bolt holes. I'm going to insert a bearing load in the vertical direction using the component method again and apply 150 pound force. So this will be shared between the 8 bolt holes. Let's go ahead and insert a couple of typical results items such as total deformation and equivalent stresses. Now we can go ahead and solve the model. It has finished solving. Let's go ahead and review the results. You can animate the total deformation, and as you can see, the moment load dominates. And then if we look at the equivalent stresses in the model, as expected, the maximum stress occurs on the corner transition between the bearing surface and the next step on the hub. And as you can see, the maximum equivalent stress is 15,000 psi, which is much less than the yield stress of structural steel. So we know that we can use the stress life method for this particular fatigue analysis. Let's go ahead and insert the fatigue tool under solution in the tree. By default, the details of the fatigue tool have been populated with certain options. Let's review them one by one. The first option is the fatigue strength factor. As we know, the SN curves would have been obtained at a specific environmental condition such as temperature using uniaxial tests and fully reversed loading. But if the operating condition of the part is drastically different than the experimental conditions, then you can use the fatigue strength factor as a strength reduction on the SN curve. Next one is the loading type. By default, the fatigue tool assumes that the loading is fully reversed. It's graphically represented here on the right. So as you can see, it assumes you're going to apply the bearing load and moment, which is an amplitude factor of 1, and then you're going to fully reverse the load in the negative direction and then back up to the full load, constituting one cycle. This assumes that the mean stress is 0. The next option in the details view is the scale factor. So this is used to explore a load higher or lower than what you've applied. So for example, you've applied 300 pound-feet of torque and a certain bearing load, and if you want to know what the fatigue results would be at 400 pound-feet of torque and a scale bearing load, you can do so. Next one is display time, which is by default is the end time or the last substep of your analysis. And then analysis type, as we discussed, since the stresses are low, we can go with the stress life option. Since the loads are fully reversed and the mean stress is 0, we don't have to choose any mean stress theory. The stress component, which will be compared against the SN curve, can be left to be equivalent stress for the moment. We will revisit that later. Now let's go ahead and insert a few fatigue results. The first one is fatigue life. You can scope to all bodies or just certain features in your model for the same. So let's go ahead and evaluate the results. So what this is telling us is, based off of this equivalent stress of 15,000 psi, looking up the SN curve, the life of the part is predicted to be a minimum of 3.4 e power 5 cycles. This means the part can survive 3.4 e power 5 cycles of fully reversed bearing and moment loads. So again, depending on what context you are designing this hub for, so this moment could have been obtained from a stop-start of the car, so which means based on the mass of the car and velocity squared and the radius of the tires, friction coefficient between the tires and the road surface and so on, you might have obtained this moment load. So it means it can survive 3.4 e power 5 cycles of stop start of the car, for example. Or if the moment load is the torque supplied to the hub during normal running of the car, then this number of cycles and the radius of the wheel can be used to back calculate how many miles the car could travel before the hub fails due to fatigue. The next result item available under the fatigue tool is the damage factor. So the damage factor is basically the ratio of the number of cycles that you consider as infinite life. So in this case, 1 e power 9 cycles versus the number of cycles the part can actually survive. The next result item is a safety factor. So again, based off of 1 e power 9 cycles, we are saying the safety factor of the part is 0.83. Or another way of looking at it is to insert a new fatigue tool and then using a scale factor equal to the safety factor of 0.83, 83075, and then inserting a fatigue life, which will give you the design life of your SN curve, or the number of cycles for the lowest stress value you have entered in engineering data. The next result item is biaxiality indicator. So this tells you whether the loading experienced by the model is pure uniaxial or pure biaxial or pure shear. So this result will help you decide whether you want to include any multi-stress correction factors. A value of -1 indicates that that region is in pure shear. A value of 0 indicates it's in uniaxial condition, and a value of 1 indicates biaxiality. So as expected, since the torque load dominates, the corner of the hub which sees the maximum stress is actually under pure shear or a biaxiality factor of -1. This tells us that we need to go into our fatigue tool and instead of using equivalent stress, we need to use the maximum shear stress value to make a more conservative estimate of the fatigue life. So with the equivalent stress, we got 3.4 e power 5. Now with this change in stress component, we see that it predicts a lower life of 1.6 e power 5, which is basically more conservative. The next fatigue tool is equivalent alternating stress. So with the current settings, the stresses are alternating between positive 17,300 psi and negative 17,300 psi. Now let's explore few other options available under the fatigue tool. So the loading type by default is fully reversed. The other options available are zero-based loading or entering a ratio or importing history-based data. If we choose zero-based, It means the load is ramped to the highest value and then it's removed and brought back to zero and then ramped back up again. So here, as you can see, the mean stress is not equal to zero. So we would have to include some type of mean stress correction. Under the mean stress theory, the various options available are the Goodman, Soderberg, Gerber, or you can enter different mean stress values versus your SN curves. So Goodman is typically used for brittle materials. Gerber is used for ductile materials. Soderberg is too conservative compared to the other so the typical recommendation would be to go with the Goodman option. Let's go ahead and re-evaluate the model. If you look at the equivalent alternating stress is not as high compared to the fully reversed loading, since it's only the excessive stress oscillating about the mean stress value, so the amplitude is much lower in this case. So if you look at the life plot, because of the low alternating stress, the life predicted is infinite, or in this case 1 e power 6. Safety factor is greater than 1, which means the part is safe. Other loading types available are ratio, where you can enter the ratio of loading number 2 with respect to loading number 1. So let's say you're applying 300 pound-feet and then you're reversing it down to 150 pound-feet and then ramping it back up to 300 pound-feet. Then you would enter a ratio of 0.5. You can also import history-based data in case you have strain gauge inputs of the amplitude with respect to time for your particular loading. So the equivalent alternating stress is not a valid result item anymore for this particular load type. So let's go ahead and evaluate the results. So this is a more advanced loading type which does rain flow counting because we don't know what combination of loadings or amplitudes are going to cause the maximum damage. So it has to do cycle counting in a more advanced way, and then it's telling you that the life of the part is going to be 411 cycles if it's subjected to that particular variable amplitude loading. That concludes our demo session. Thanks for watching.